Hey, welcome back, AP Calculus students. Today we're looking at 6.4, Fundamental Theorem of Calculus. So it looks really complex and it sounds super important, and it is. But this is what the Fundamental Theorem of Calculus looks like. So it's saying F, capital F. So anytime you see capital F, that means the antiderivative, which is what we're focusing on for the second semester of calculus. What it's equal to is the integral from a, so a is some constant, to an unknown value x of f of t dt. So it's just saying that the antiderivative is the integral. And then the second part of this says that if we do the derivative of our antiderivative, right, because capital F represents the antiderivative, it's equal to, so this part is the derivative and the integral, this part is the antiderivative, right? So what it's saying is it undoes, it's right here, antiderivative undoes the derivative. Oops, that's gross. And vice versa. Okay, so the first two are really easy. So it's just playing off the idea of the derivative and the integral. So and the antiderivative, I should say. So for these ones, if the bottom is a constant and the top is an x, all we have to do here, right, because we're finding the derivative of the antiderivative, is say this is going to be cosine x for our simplified version. Okay, likewise for the second one, because we have a constant here and an x here, then all we do is take our function and replace t with an x. So super easy and straightforward. It's just demonstrating that if the bottom is a constant of our integral, if our start is a constant, excuse me, and the top is just x, then it's the function. The integral and the derivative undo each other. Okay, so this one's a little bit trickier. Right, so for this one, it's asking us to find the derivative of our integral. Yes, the bottom is a constant, but the end part is x squared. So this is going to change it a little bit. So what we're going to have to do is we're going to do cosine, and then we can put our x squared in for t, right? But we need to also do the derivative. Well, actually, let's say this. So let's say this is u. We're going to call it u for now because we can find the derivative of that. So we're going to do the derivative is cosine u. But remember when we said we have an inside function, right? So our inside function is u. We also have to do the du with respect to x. X? Yeah, x. Okay, so that just means that we're going to do the derivative of our u, right? So our u is x squared, our du is 2x. So we just need to tack on for our du dx the 2x. So we're going to have 2x cosine, and then we can replace the u with our x squared. So this is like the long version of it and the fully explained version of it. But yeah, you can skip the middle steps if all you have to do is remember to do this little chain here where we do the derivative of our inside. Okay, next example. So notice this one is flip-flopped, right? So our bottom, our starting point is x and our ending point is 5. So what we're going to do is we're going to use one of the rules that we talked about a couple of lessons ago, where we said that we can switch the start and the end points if we if we change our sign to negative. So we're going to go ahead and do that. So we're going to put the x on top. We're going to put the 5 on bottom. I'm just going to take the negative of it. 3t sine t dt. And then now we're good, right? This is not an x squared or anything funky. It's just x. And the bottom is a constant. So we can just go ahead and say that this, the derivative, right? We're finding derivative with respect to x of this thing. That's going to be equal to, and we're just going to substitute the x, right? So 3x sine x. Okay, on to a little bit more complicated one. So this one's got no constants in it, right? So it's got an x squared as our end, a 2x as our beginning. So what we're going to do here is two things, right? So we're going to split this up. So using one of the rules again that we were talking about a few lessons ago, we're going to split this up and we're going to just say, let's go from 0 to x squared. And then let's go from 2x to 0. So we're just splitting up this integral into two parts. Now notice that the 2x still is on the bottom and the x squared is still on the top, and we're just saying that whatever 2x is, it goes to 0, and then it starts back up from 0 to x squared. So this is like the same thing as this, just in two parts, from 2x to 0, then from 0 to x squared. And then now we're going to apply that rule that we did last time, right? If our variable is in the bottom and our constant's at the top, in order for us to apply the fundamental theorem of calculus, it's got to be flip-flopped. So we're going to change this to a minus then, so we can bring the 2x to the top and the 0 to the bottom, which satisfies the requirements for the fundamental theorem of calculus. The first part does not need to be changed because our variable is on the top. Okay, and then now we can find the derivative with respect to x of this whole thing. So we're going to skip steps here, right? So we know that this is going to be 1 over 2 plus e to the, we're replacing the t with the x squared, sorry, because we're going to x squared. And we just need to remember to chain that x squared, so we have 2x. Okay, likewise for the second one, we're going to replace the t with 2x. And because it's not just x up here that we're replacing, we got to chain it. So the derivative of 2x is 2. Okay, so this would be our derivative using the ideas that we took from the fundamental theorem of calculus. Okay, and then the last one is pretty easy. So it's kind of, it's wordy, but the application of it, the what word am I looking for? The execution of it is really pretty simple. So it says find the function y equals f of x with derivative dy dx equals tangent x that satisfies f of 3 equals 5. Okay, so what we're going to do here is we're going to do, okay, we want to start at 3, right? X is 3. So we'll put 3 as our start. We'll put our x on the top. We'll say tangent x. And then we'll say this 5, we're just going to add it on. Dx. Now, why this works under the fundamental theorem of calculus is because if I plug a 3 in here, right, if I put a 3 here, we know that if our start and end points are the same, there's no area under the curve because there's no interval, right? The start and end point are the same place. So this whole thing right here is going to be 0. And then when we get our 5, 0 plus 5 is 5. So it satisfies this part because when we plug in a 3, when we insert the 3 into our integral, then the whole tangent part becomes 0, and then we just have 5, which is what our output should be. So very simple. So again, we take the exact same function, right, as long as it says with derivative, right? We do our integral on it using the fundamental theorem of calculus idea. We're going to put our start, or not our start, well, yeah, it is our start, but our x value here, that's given. We're going to put our x on top, and then this is just going to be your y from the initial part of the problem where it's saying f of 3 equals 5. Okay, so hopefully that's not too bad. We're going to start getting into more antiderivative integral stuff next time. In fact, I think we're going to introduce the power rule. I'm going to do it a little bit early because I don't think they quite do it yet, but I think it's valuable to do so. So just a little heads up as we're moving forward. Good job today.